It's loaded now, and so I'm going to talk about real-time payments using Erlang. Talk a little bit about how we use Erlang at our company to make credit card payments. And I've been working with Erlang for 4 years now. Started as a student at Uppsala University in Sweden, using Erlang in some student projects, and then I spent a few years at Erlang Solutions, and then I moved to Berlin last year to begin at SumUp. So I'm gonna go through what SumUp is, and then we get some pretty pictures, and we'll see a bit about our system architecture, our Erlang components, what kind of things we do for fault tolerance, and the next architecture that we're building right now, and some of the things that we learned by using Erlang. Right, so what is SumUp? Well, it's a mobile card payments company, and it was founded in 2011, and it's grown quite quickly, so there's 130 employees right now. We're deployed in 10 countries. We started the deployment after a 4-month closed beta last year, and deployed in the UK, Ireland, Germany, and Austria in late August last year. And then in November we launched in Italy, Spain, and the Netherlands. And then later on, before Christmas, we launched in France, Belgium, and Portugal. And we use a Erlang / Ruby backend. And we have development teams in Berlin, Dublin, and Sofia in Bulgaria. Right, so this is a picture of our card reader connected to an iPad. We had this one with us as well, so later on you can try it out if you want to try some real transactions. It's if you want to do that, it'd probably be like a €1 transaction, and it always goes to charity when we do it at events. So yeah. Right. So this is a very photoshopped picture from our marketing department, showing how to use our product. Basically, the idea is that we have Android and iOS apps, which we give you download them if you're a merchant, if you have a cafe or small business, and then you can add your products to it, like ice cream, and you can in the mobile app you select products. The end customer selects products, and then can choose to add tip amounts, and then choose which payment method they want to use. And there's another picture of signing. This is a screenshot of the mobile app where you just added 3 products, and you get the total, and if there's a local tax in that country. And then you can just press charge to make a purchase. Right, and then it goes into the cloud, which means that it actually goes to a Ruby rack server, or whatever connection you have with your mobile device. And this component will perform some business-related checks, and then it will talk to our Erlang backend, which will then later on talk to banks or third-party acquirers in the payment industry. So just to show here another picture there. Basically, we have this Ruby component where we have a lot of API calls for sign up to log into the system if you're a merchant, to do various kinds of calls to our backend, and also to make the actual purchase. And then if you do a real purchase, then this component will forward that payment request to our internal payment processing, which will be handled by JAWS web server. As we use HTTP between our Ruby components and Erlang components right now. And after it has received that, it will continue with the payment processing. And I will show a bit later on which Erlang components we have and what kind of responsibilities they have in the payment flow. But before I show those Erlang components, I just want to mention something about PCI. When you make computer systems and deal with credit card data, you have some very strict requirements on how you deal with that data, because you don't want to randomly display a full credit card number. And there are rules about how you set up the network, what kind of firewalls rules you have, how components can talk to each other, how you can store things in memory, how you can store things in disk. It's a big document, but it's something you have to follow when you handle credit card data. And we have audits 4 times a year, which will check each requirement. And the requirement specification itself is public. So if you're in the PCI zone in a computer system and you have certified that component, then you can deal with the full credit card number, which you need to do in some cases. You need a full number if you need to talk to a bank, for example, and finalize the actual transaction. You might also need the CV2 code and the expiry dates. But if you are outside of the PCI zone in your system, you have to apply certain rules. For example, one important requirement is that if you're outside of it, you can show a maximum of 6 digits at the beginning of your credit card number and the last 4. But you can't show anything more than that, so you have to mask out that data in between. And often you only need the first 4 ones, which is why on many receipts, if you're in a restaurant and you pay with your credit card, you might see your credit card number masked on the receipt that you get. So basically, these 2 different areas is what has guided our system design. So first of all, the mobile device, the reader will actually read the card data from your credit card, and then it will forward that to our backend components. And there we are handling the actual card data. So in order to have system components which do not have to be certified by this PCI standard, we use a token server to tokenize the card data. So we apply some hashing on the card number to get a unique token which we can use in other parts of our system to represent one unique credit card, but it's not represented by its card number, it's by a unique token. So the first thing we do is that we tokenize all the card data, and then once we have the token, we can send it outside this PCI certified zone and do more business logic, more application specific stuff. And the entire point between splitting up the system in these 2 parts is that the PCI audit will be shorter because there's less code to audit, and there's also a security issue many security issues related with this. You want as few components as possible that actually deal with the card data. It doesn't make sense to throw around credit card data all over your system if only a few pieces need it. So we send it outside, and then we do some fraud detection, which fetches data from our SQL database and also from a non-PCI React instance, which we have. And these fraud checks are, it can be basic things like, is this card blocked in this country? Is this card range blocked in this country? But it can also be more advanced algorithms where we look at behaviors of certain cards. Once we are done with our fraud detection and other business logic, we send the request back into the PCI zone to our processing server, which will use the token to fetch the actual card data that was stored by the token server in a PCI React instance. So when we first tokenize the data, we actually store the real data in memory for a limited amount of time, and then retrieve it later on when we are back in that zone. And then the processing server will talk to the actual bank which issued your card to then finalize the transaction. So that's just the basic overview, and we have some other components which can talk to the SQL database, where we have more relational data. Like we have a operations interface that wants to make queries over past transactions, which maps quite well to SQL. And then each merchant can also access a merchant web interface to see a list of all of their transactions. Right. So we have some Erlang nodes in our system. We used the rebar create node to make a template. We have multiple Erlang applications. We try to structure the functionality into Erlang applications so that one major functionality is one Erlang application, which we then fetch into a release node using the rebar dependencies. And it's a very, very nice way, because then it's easy to structure functionality, and you can specify, for example, a git tag in the rebar dependency, so you will always be sure that that dependency will not change unless you update the tag. And it's really nice for when you release a component, so you don't just pull in the dependency from the master branch and see what happens. And each node has some unit testing. We use unit, common test. We have a few property tests, but not much property-based testing right now. And we also use Lagger from Basho for all of our logging. So the first Erlang component is the token server, and when it receives the encrypted card data, it will perform decryption and also encryption for storing some card data for long term, and it will also put it into memory for the limited amount of the payment transaction. We will do the tokenization of the primary account number, which is the 16 digits on your card. And for some future card readers, we will also need to attach a special hardware which will be attached to this node when we do transactions with the chip in the card. Right now we are only reading the data from the chip and from the magnetic stripe. We are not actually communicating with the chip in the card. And right, so that's one of our components. Then I mentioned the fraud server. We can block things on bin ranges for cards. We also have a lot of limits a merchant has a certain limit for a day or for a week, longer periods of times. Some of our algorithms are stateful, some are stateless. This bin ranging, for example, doesn't care about the history of the merchant or the history of one particular credit card. It will just look at the first 6 numbers and see if it matches the rule. But some of the more advanced algorithms will have a state. You want to track behaviors of a individual card. If a merchant which has registered as a taxi driver suddenly starts receiving credit card transactions for millions of euro, you probably want to detect that somehow. And there's basically two operations or two outcomes of the fraud server for each transaction. There's either a full blocking of the transaction when we just say that we block it, or we will flag it because it triggered certain flags in how the history looks like for that merchant or that card or some combination of that. And this component is outside the PCI zone, so it doesn't have access to the full credit card data. Right, and the component that actually talks to your bank, the processing server, it has connections to several third-party entities in the payment industry, and it can perform authorization of a payment transaction. Capture it means actually move money between accounts, refund transactions, and other types of transactions. There is sometimes you might have to connect to a certain acquirer or a certain bank. Sometimes there might be a choice for us, which we can perform based on which country the transaction is in, and other variables which we have on the merchant and the history of that credit card. In each of our Erlang components, we have quite simple supervisor trees. The main idea is to encapsulate one transaction in one Erlang process, so that we don't run several transactions in a single process. We use a simple one-for-one supervised behavior. If there is a bug, if something crashes, it should only ever affect one single transaction. That's the main idea. And the flow when you have several transactions makes it quite easy to use to separate it into Erlang processes, because multiple transactions are independent of each other. And then the services, for example, the tokenization in the token server, or the different fraud detection algorithms in the fraud server, we're using the gen server behavior in a simple supervisor tree. For services where it makes sense to simply just restart it, so it works for the next transaction if something were to crash for a previous one. We use the Linux virtual server to have IP level load balancing between nodes. Right. For our React instances, we have a number of replicas and same amount plus 1 nodes. Very important for us that if some machines go down, we can still use the system. And the React configuration we use is not optimized for load or performance. It's purely for fault tolerance. The SQL database has just a primary slave configuration. And this is our new architecture, where our idea is to improve some of the things which are in our current system. We want to, for payments, we want to remove this legacy Ruby component to handle the first request and handle that in a Erlang gateway instead, which will handle different communication protocols and then translate that into a generic transaction request. So right now we're working on two new components for a new transaction gateway and a new server for handling these different things. We want to switch some of our more complex gen servers to finite state machine behaviors, maybe using genFSM, but probably using a custom behavior which is based on genFSM, but where we might have added things like persistent states. We also want to add non-real-time processing to our Erlang processing component to be able to do things like batch file handling and different types of transactions that occur that you might batch together for one day, for example. Some of the things we learned is that rebar is a really nice tool. The way to structure one major functionality into one Erlang application using rebar is really nice, and then pull that into a release node repository using the rebar configuration with the dependencies. That has worked really well for us and simplified our deployment. Gen server versus genFSM can be a difficult choice when the state is not a simple one. If you have a really simple state, it might make more sense to have a gen server, but when that state grows and you start to manipulate that state in different state transitions, it sometimes makes sense to refactor that into a genFSM. So that's something we are learning more about. The Erlang functional style has really helped us in the backend. The top-bottom approach, where we have a callback function for each request and just use the functional style of Erlang, is really nice. And I think we benefit a lot from having a clear separation between side effect-free functions and functions which actually do have side effects. It helps a lot when you reason about payment transactions, and it also makes it very easy to modify critical code that deals with car data, for example. When you know that, okay, this function is completely side effect free, it will just take an input and give it back to the caller. The binary handling has been really useful when we deal with things like acquire protocols. There are some really old protocols for how you wrap the car data when you talk to payment acquirers. So, for example, the combination of the bit syntax and the binary module is really something that makes you happy when you code Erlang. And some of our code for handling these binary protocols, I think, would have been much longer in other languages compared to Erlang. As I said, the functional style in general, I think, is something that is really useful when you code these types of backend systems. So this is just an example of length field in a tile length value structure that we had to decode. Some other things learned. Erlang node design can be difficult when you have multiple nodes and you split them between different areas of your system. when should you have a single node and when should you split it up in several nodes. The separation between NoSQL and SQL has been a challenge. We had basically requirements that we had to use a SQL database for parts of the transaction data, and to combine that with NoSQL is very much a ongoing process. And for deployment, we actually tried to use Rebar to generate these rel-tool upgrade files, generate the rel-up file, and we tried it for components, and it actually works fine to use this for releases. But then our sysadmin preferred to restart the entire node behind the load balancer instead, which means that we are not using it right now, but it would be nice to use it sometime in the future. And I think it's always nice to design the node so that you can actually use it. Right, so the future, we have a second iteration of our architecture where we try to address some of the problems we have with how we use Erlang right now. We will most likely move into using multiple data centers, try to connect that. We have a consumer app, which right now the Android and iOS apps, they're only for merchants, so they're only for business owners who then charge their end customers using those apps. But we also have a mobile app for the end customer itself, which it was demoed recently on the Finovate financial conference. So we have a prototype, and it's basically the idea that if you trust a merchant, like you trust your local coffee cafeteria, then you can download the consumer app, connect that to the merchant's app, and then you can use the geolocation updates in Android and iOS to automatically have the merchant make a transaction on your credit card, because you trust them to only charge you once for the coffee. So that's something which we have in the works. We also have new card readers to be able to talk to the chip in the card, which is called EMV. We also have some new readers for supporting PIN, so you can actually enter the PIN when you make a transaction. Right, so that's pretty much what I had. And if you have any questions, just ask them. And these are the emails for we from SumUp are here today. Right, so do you have any questions? Yes.
When you said you wanted to move from GenServer to GenFSM, did you consider just writing plain Erlang in its state?
Yeah,
because then you can get selective receive, which is really neat.
Indeed, and we tried. We haven't decided yet exactly which route we're going there, but we tried to use GenServer. We also tried to define our own GenServer behavior using plain Erlang, and we're not really sure exactly how we're going to use it right now. We have a prototype which is not using GenServer. It's basically our own GenServer implementation, and it's not an easy choice always, because the good thing about the GenServer behavior is that it's really well tested. So that's one thing to consider. But
I didn't mean writing our own GenServer behavior. I mean just writing the state machine as Erlang functions. Like plain Erlang.
Oh.
Like one function per state and receive. And you could use the message sending functionality from Gen directly, you can call it.
Right, you could.
Monitoring thing.
But I think if we do that, we're probably on our way to building a behavior as well. So.
Yeah, there is actually plain FSM with Vega. to give you the OTP compatibility.
Right.
And then you can write your own.
Yes, you can fill it in the OTP tree. Yeah.
Just question about security. You just managed to read quite some articles about all fraud that happens with credit cards. So how customer feel when you just have to plug in his credit card in some strange device attached to whatever tablet that could be influenced by virus and so on. They have some device that show you kind of trust. Should be isolated somehow. In this case, you really just plug in the smart card in smartphone, you don't know what happened there. That could be that just immediately stream follows around.
Right, it's a good point, and basically there are two ways you can go there. Either you can have the reader itself encrypt the data, and then the mobile app couldn't look at it even if you tried to, and then decrypt it at the backend, which we have for we have encrypted card readers. The other way is if you use a unencrypted card reader, then you would have to trust the mobile app to make a proper encryption before sending it. So there is of course a higher risk if you allow the mobile app to do the encryption rather than the actual hardware. So that's definitely one concern, and it is an entirely new industry to do this mobile payment. So there's a lot of work to get merchants on board. Some merchants are more concerned than others with how much they trust this new security.
But from user point of view, just okay, merchants could show them software, but like user, I'm in the shop and then some people just take my card and plug into smartphone actually.
Right. Well, it is of course. I mean, I can understand how it feels insecure if you do it, but on the other hand, you have been plugged. You have plugged in your card into these existing terminals for a long time, and it's basically at the end of the day, it's the same thing. Do you trust the terminal that you use, whether the terminal is a old school terminal or if it's the mobile app plus the reader combination? So at the end of the day, you still have to trust whoever you give your card to. Yep.
I think you just answered my question, but I know some first generation, the mobile app was in the PCI zone. In the second generation, it was not. Is it because of an card reader that allows it to be?
No, that's just my presentation skills which failed. The mobile app has to be certified in both generations, but we want to move into a system where we do all encryption on the reader level, so that we have less of concern in the mobile app. Yep.
This certification, how does that work? Who comes out and do they kind of look at your code to see that it actually works? There are these third-party payment auditors, and they in turn are approved by Visa or MasterCard, Amex, other card schemes and banks. So the card scheme says that, okay, we trust this auditor, and then that auditor will, there are several things. They're looking at the code, verifying that, following the code flow, looking at what it does when it deals with the card numbers. It's also a lot to look at the workflow, like who can make a change to the code. Do you have to create a JIRA ticket? Someone has to approve it. And also the actual physical setup of the network. So they look at everything basically. So they know Erlang now?
That's a good question. I think they're getting better at Erlang.
Is your architecture now fully Erlang, or are there other moving parts, right parts?
It's still a combination of Erlang and Ruby components. And for the payment flow itself, we want to move to use only Erlang, but we will still keep some components. For example, the merchant web interface that we have makes more sense to have in Ruby because it only talks to the SQL database, and there are a lot of Ruby on Rails things which makes more sense in that component. So I think we will keep using both languages.
similar or branch of Square US?
Yes, it's some people call it a clone. It's we basically do what they do, but for the European market. And the thing is, aside from the software, it's a lot of legal issues that you have to solve, and that's why Square is not yet deployed in Europe. So, we're basically using their ID, but then trying to extend it as well with the consumer app, for example.